Welcome to 1007 ICT, 1807 ICT, and 7611 ICT, Computer Systems and Networks. This is Lecture 6A, Memory Organization. And so last time we covered decimal real numbers, we looked at fixed point binary, converting fractions, floating point numbers. We also looked in a little bit of detail at the IEEE floating point formats, particularly the 32-bit IEEE 754 floating point format. In this lecture, we're going to look at addressing, the idea of endianness, primary memory and secondary memory. So, looking at the learning objectives, you'll notice that you'll see gained an understanding of, we're getting some insight into how this stuff works. We're not necessarily doing much processing based on this. Lecture 3B will have a bit more processing based stuff that you'll be looking at. So the first thing we look at is data size versus addressing quanta. Okay, that sounds quite wordy. The resolution of the addressing may be different from the amount of data fetched in one go. So what that's saying is that when you're accessing memory, you might be able to access 1 byte at a time. So you might be able to access location 5, location 6, location 7, for example. But because you're using a 32-bit machine, for example, you might only be able to access 32 bits at a time. So starting at a particular memory location, you might be able to access any byte individually, but when you get to that byte, you would grab a certain number of bits. It might not be 8 bits, it might be more. So many computers use byte level addressing so that it's possible to address down to the individual byte. You can get any memory location down to the byte level, but when you grab information, for example, if you have a 32-bit machine, you tend to grab 32 bits at a time. If you had a 64-bit machine, how many bits do you think you would grab at a time? 64. It just depends on the architecture that you're working with. Now that actually causes some problems or challenges, and I'll talk about those in a little bit of detail of the next few sections. So what we're talking about here is I've got my memory. Let me try that again. I have my memory here. Alright. I can draw. Technology, right? Okay, so apparently I can draw on this this diagram, if it'll let me. I think it will now. And so what we're talking about here is we have some memory. We have some memory locations. Let's say 0, 1, 2, 3, 4, 5, 6, 7. Okay, so there's 8 memory locations in memory. They're individual bytes. Each block here has 8 bits, and I can grab at the byte level. So what I'm going to do is I'll illustrate here. Imagine that I'm getting this location. I'm starting to grab information from location A. If I'm grabbing 1 byte, I would just grab this. If I'm grabbing 2 bytes, well, I grab this, and probably I'll grab the next one in memory as well, right? So I'll grab A and B, 2 bytes. So what this is saying is I can grab any, or I can start at any byte, but I can grab multiple bytes when I get there. This is not the only way that I could grab stuff from memory. I could also grab stuff from here and the previous one. Is that also possible? It's possible, yeah. If I'm grabbing 2 bytes at a time, I could grab from here backwards or here forwards. There's different orientations I could choose. Now, if I grab from here and there, A and B, then if I read from address A first, I will get 0, 0, 0, 1, 1, 0, 0, 0, 1, 1, 0, 0, 1, 0, 1, 1. Lots of ones and zeros, but you can see the sequence that I've gone through, right? Alternatively, if I grab them from A and B like this, I could read from B, so I could get 1, 1, 0, 0, 1, 0, 1, 1, 0, 0, 0, 1, 1, 0, 0, 0. Is that also possible? It's possible, right? It just depends on where I start reading from. Does that make sense? So are those two numbers the same? If I start reading from A or if I start reading from B, are they going to be the same or are they going to be different? They're going to be different. So I have to decide consistently where I start reading from. That's the first problem. Do you think everyone reads from the same position? Probably not. Right, you can see a challenge here, right? So because we have options, some people will choose one option, some people will choose a different option. And that's actually what we're going to talk about in the next little section. So here's a discussion on the byte addressing of words. So in this example, the address specifies the least significant byte, and this is going to be called little endian. Now, before I go into this diagram, I think this diagram will make a lot more sense if we look at an example. And so the example I'm going to look at is, well, what are the options? Right, and I already alluded to a couple of these. Imagine that my memory location is 12. So here's my memory location. I'm going to look at this one on the left here. And I want to read 2 bytes. I have a number of options. I've got them all lined up here, so all the different options. The first options will be I'll start here and I'll go this way, and I'm going to get A and B. Make sense? It's the option to read it. And actually, the A is the big part of it. It's the first part. And B is the little part of the number. It's the smaller part. Why do I say big and little? Well, this starts at 1, 2, 4, 8, 16. You'll notice as I go this way, it gets bigger and bigger and bigger. So on the left, we've got the big end, and on the right, we have the little end in terms of values that those columns are worth. That's the first one. The first one's pretty easy. Start at 12, and I just go up, A and B. Cool. Next one, I start at 12, and I don't start at A, but I start one up, and I go down. This is another way I could read it. This is a little more tricky, but it's possible. And if I did that, I would get BA, yeah? This is the little end, this is the big end. Does that make sense? If I read this one first, and I put it on the big end, it's the first one, yeah? Okay, some other options. Well, if I start at 12, I could also go AC, yeah? Or I could go CA, going the opposite of this one over here. I could start at 12, and I could start reading at the C and then go backwards that way. That's the other option. So those 2 options. I'll point out that we don't use these 2 options in our discussion, so we can ignore them. But are they possible? Yes, they're possible. We just don't use them, actually. So the 2 options we have left are big endian and little endian. For people, big endian is really natural. I start at 12. This is the big end, and I just read from left to right. That's really nice. Yep. For machines or certain kinds of operations of machines, this one, the little endian, might be more efficient. So you can have 2 different models. And actually, I can read it the same way, by the way. If I start here, rather than going one up and going down, I can say, look, A is the little end. And when I go up one, I put it to the left of it, and I go up one, I put it to the left of that, and so on. You can see I can build up a bigger number that way. Okay, what I've done at the moment, I'm just describing the different ways we can achieve reading a number from memory. This only happens if I'm reading multiple bytes. If I'm only reading a single byte, are there any problems? There's only one way to read a single byte. Yep, so, okay. We will continue with this discussion in this bigger diagram, and we're talking here about the little endian, or least significant byte, is where we start. So when I'm fetching 16 bits at an address, I will get a particular answer from this table. So let's look at the table. I'll draw on it. I think it'll be quicker and easier to describe that. If I'm fetching 16 bits at address 0, and I'm using this little endian organization, and what that basically is saying is the little end is first. So I'm looking at byte 0. I get there. How many bits do I need? 16. That's 2 of these rows. So I need byte 0 and byte 1. The little end is at byte 0. So I'm going to write down 0C here, and then I go up 1, and I've got 1A, and I'm going to write 1A to the left of it, because 0C is the little end. It happens to be first, but I'm using it as a little end. And as I go up, I'll add 1A to the left of it. Why is 1A to the left of that? Because it's bigger. And in our binary numbers, 1, 2, 4, 8, 16, as we go to the left, we get bigger values. Okay, so we'll see a couple of other examples. 16-bit words at address 2. Where's address 2? Here. Again, this is little endian. 4, 7. There's 2 bytes. 2, 9. We just build it up bit by bit. Next one, 16-bit word at address 1. So this one's indicating that you don't necessarily have to be on an even number of bytes. You can read odd number of bytes as well. So start at 1, here's 1. It's little endian. How many bits do I need? 16 bits, so it's these two, 1A and 47 to the left of it. Then the last one, this is a bigger one. We start at address 5. Here we go. And we fetch how many bits? 32 bits. So how many of these boxes do I need? I need 4 of them, because there's 8 bits in each box. So little end is here, 1-8. The next one, 3-4, is to the left of it. The next one, 8E, is to the left of it. That's a 4, not a 9. And the next one is 5-2 to the left of it. Can you see I'm just building up a bigger number? This is not natural for people. Yes? It's the opposite of what we would like. Do you think there's also something called big endian? If there's a little endian? Yeah? And so if we were using big endian, and if I said, let me just get rid of this stuff down the bottom here. If I said big endian and get 16 bits at address, I don't know, 3. Where's address 3? Address 3 is here. And I want 16 bits. How many boxes do I need? 2. And the big end is at the start. I'm using big endian. So I have 2, 9, and CB. This is much more natural for a person. This is what we would expect. Do you think the machine cares about what we expect? Not even a little bit. So if something's more efficient, we will use a more efficient construction. Okay. I recognize that little endian is a bit strange, right? Because we don't normally write words or numbers that way, but it is a valid way to store numbers inside the machine. So this example, that table there, basically just shows you little endian addressing. We'll talk about big endian in a little bit more detail later. Next thing we look at is word alignment. So if you imagine a byte address computer with 32-bit words, that basically means that I can access any memory location to the byte level. So if I want byte 5, I can go there. Want byte 37, I can go there. But I have a 32-bit machine, so when I grab something, I grab 32 bits. Okay. Some CPUs may allow words to be stored across 32-bit boundaries. So they might say, well, look, you can start on 5. Okay, 5, 6, 7, 8 would be your values. Is 5 a multiple of 4? What do you think? Answer is no. Why did I say multiple of 4? How many bytes are in 32 bits? How many bytes? How many bits in a byte? It's not a trick question. 8 bits in a byte? Yep. So how many bytes are in 32 bits? 4 bytes. So ideally, the machine would work in multiples of 4 bytes. Yeah. So byte 0 would be a good place to start. Byte 4, byte 8, byte 12, byte 16. What about byte 5? It's possible, but it may not be as efficient. I'll show you why not. So the CPU may allow you to do that, but the operating system may say, look, that's not very efficient for me. When I'm grabbing 32 bits, I'd like it to be on an even multiple of 4. So let's have a look at how that looks as a diagram. Here are my addresses. So look, address 0, this is address 0, this is address 1, 2, 3. So this is just a memory table, but a little bit compressed. 4, 5, 6, 7, 8, 9. Yeah, you see how this works? Okay, so there's 4 bytes across each row. If I store my 4 bytes, or if I say I'm going to grab something at location 16, I will grab these 4 bytes. How many bits is that? That's 32 bits. It's a 32-bit machine. I'll grab that information, and it's the information that I need, actually. How many reads did I need to do to get that 32 bits? Just one. When I go to block 16 or address 16, I just grab 32 bits from there. It's one read. Have a look at this organization here, where I've got something in 16 and 20 here. These are my 2 rows. This is location 16, 17, 18, 19, and 20. That's what they're labeled. If I read something at location 16, 16 is a multiple of 4. I need to read from multiples of 4. Just imagine it's a big stamp. It just grabs stuff at, regular locations. I grab these 4 bytes. Is this the information that I want? Not quite. I'm missing 1. I can't just read 1 byte, so I have to read the whole row there. How many rows did I need to read here? 2. How many rows did I have to read here? 1. So this one is the same. Because my data is kind of scattered and it's not at a multiple of 4, it's more expensive to read it. 2 reads instead of 1. I've just halved the speed of the machine. Does that make sense? All right, same with the last one. So which one is the preferred way to organize stuff? The first one, and that means that we have to be careful where we put things, and in particular, if I have a 32-bit machine which works on 4 bytes, I should be at a multiple of 4. Right, to make it as efficient as possible to do the reading. Do you ever see this level of organization when you're working with your computer? Unlikely, right? So it's all happening underneath the hood. So there are some good choices we can make and there are some poor choices. The operating system may require that we make the good choices. The CPU might say, that's fine, you can put it wherever you want. You see the difference? Okay. Here's an example of the word alignment. So the Intel architecture, the 32-bit version of that, the hardware will work regardless of the alignment of the data. So the hardware will be fine. Linux as an operating system requires 2-byte data types to have an address that's a multiple of 2. So if you've got something that's 2 bytes big, must be a multiple of 2. Larger data types must have an address that's a multiple of 4. So 3 and 4 would be multiples of 4. 5 would be multiples of 4, yeah, anything bigger. What about 1 byte? Are there 1 byte data types? Yes, characters are one example. And so 1 byte data types don't fit that well into this model, and probably they're upgraded to 2 bytes. So a character might take up 2 bytes instead of 1. Are you wasting some space there? Yeah, actually. So maybe we want to have some systems in place to organize our data more efficiently. Windows requires any k-byte data type to have an address that's a multiple of k. It's maybe a bit strange, but if I've got a 5-byte data type, it must be on a multiple of 5. 4 bytes, multiple of 4. So it's actually pretty easy. It just seems a little bit strange. Compilers can take care of the alignment issue, but they don't always do it in the most efficient manner. So depending on certain things going on in the environment, they may or may not do this efficiently. So here's an example. Imagine that we've got this, well, there's a struct. A struct is basically a way to glue things together. So think of it as a box. Right? So this box has 4 things in it. What are those 4 things? A character, an int, a character, and an int, in that order. Right? So they're in this specific order. How big is a character? 1 byte. How big is an int? 4 bytes. There's another character, 1 byte, another int, 4 bytes. All up, how many bytes are there? 10. Okay? If the compiler comes along and it says, I have to put these in the order that you give them to me, how will it allocate them? Well, the first thing is the character A comes in and it says, okay, I'm starting with an empty memory, so location 0 is where we start. Can my 1 byte value start here? Sure, I'll put it here. There it goes. How many bytes does it take up? 1. It's a 1 byte data type. What's the next possible location? Location 1, location 2, location 3, and then 4, 5, 6, 7, so on, right? Now I've got a 4 byte data type. My operating system says I can't put a 4 byte data type anywhere other than a multiple of 4. So is 1 a multiple of 4? 2? 3? No, where does it have to go? It has to go on the next available multiple of 4, which is 4. And it has 4 bytes to it. There it goes. Then the next one comes in, B. What's the next available location? 8. Can a 1 byte data type go there? Sure, no problem. Then there's 9, 10, 11. My next data type is an int. It's 4 bytes. Can it go at 9? No. 10, no. 11, no. 12 is the next available multiple of 4, and there it goes. Can you see the kind of logic that's being applied here? Are we able to put it here, yes or no, and it does or doesn't put it there. How many bytes does this take up? 16. That's much more than the 10 that it should take. Is that efficient? Can we pack it more efficiently? Potentially. Depends on the architecture, actually, or the environment. So imagine that I've got my struct here and I've rearranged them, and now my ints are first and then I've got my two characters. So my int is 4 bytes. 0 is a multiple of 4, yes or no? Yes, we'll treat it as 1. So yes, we can put it there. The next one, y, the next available location is 4. Can y go there? Yes. It's fine, it's a multiple of 4. The next is a character. This is a 1 byte thing, so it can fit definitely at location 8. There it is. Then the next one is b, which is a 1 byte thing, and depending on the architecture or the environment, we may be able to put it here. So let's say we can put it at a multiple of 1. There it goes. How many bytes have we taken up so far? 10. Now, I'll point out that these two you may or may not be able to use. It depends what comes next, right? If you've got an int coming next, then you can't use those two. If you've got a char coming next, then potentially you can use those two. Can you see that it's actually important about how we organize the data? And potentially you as the programmer can have some impact on that, depending on what the compiler does at a lower level, right? So going back to endianness, so the order of bytes and words can be left to right, big endian, or right to left, little endian. We already looked at this a little bit. And here we got a hexadecimal number OX12AB34CD. In big endian, it's written as 12AB34CD. In little endian, it's written as CD34AB12. They look different. Yeah, if you're just looking at them like that, they look different. Are they the same value? Yes, they're the same value. They're just written differently. So big endian data is stored from the highest order byte to the lowest. Little endian data is stored from the lowest order byte to the highest. And in either way, the leftmost bit in a byte remains the most significant. I'll talk a little bit about that because there's a little bit of detail there that we went over very quickly. So here we have some examples. Big endian and little endian. Let's try big endian, starting at location 0, 1, 2, AB, 3, 4, CD. This is how we would expect to have it written. Little endian, starting at location 0, CD, 3, 4, AB, 1, 2. So for little endian, this one, if you want to get the most important part, the big end, you have to go all the way to the top. Yeah, it's not directly accessible from you to you from down here. For big endian, if you want the big part, it's right here. Really convenient. If you want the little end, it's really far away. Can you see that depending on what you're trying to achieve, one of these may be more efficient than another one? I'll talk about that in a minute as well. But there are some differences that might imply that you can use them for certain processes. So the big end is on the left, the little end is on the right. So if computers only use bite-sized words, do they? No, you have a 64-bit machine probably at home, so it's using 64 bits instead of 8 bits, right? So if computers were restricted to 8 bits, it wouldn't be a problem, this little endian, big endian. Yeah? But because we're using multiple bits, and we have computers talking to each other, and they may use a different language, one of them might be big endian, one of them might be little endian, you're going to get some problems. So the problem is that computers historically used one or the other. So in the old days, Macs and Sun used big endian and Intel PCs used little endian. So when they try and talk to each other, they're actually talking different languages. So endianness has important implications when you're writing data to a file. If I write data to a file on my machine, and then I take that disk, for example, or transfer that file to another machine, and it's written in a different endianness, will we have problems? Yeah, we will. If there are things that are more than 1 byte big, we will have problems. If they're all 1 byte big, it's not a problem. When we're porting applications, so that basically means just translating from one architecture to another, or basically going from Mac to a Windows, for example, machine. Transferring data between two different computers via network. Do you do this stuff frequently? Yeah? Do you have any problems? Not these days, so probably we have solved this problem. Does that make sense? Yeah, so this used to be a much bigger problem than it is now, by the way. So big endian is more natural. It's easier for people to read. The sign of the number can be determined by looking at the byte at address offset 0. I'll talk about that in a second with the picture. Strings and integers are stored in the same order. That's nice. Little endian conversion from a 16-bit value to a 32-bit value doesn't require any arithmetic. And also, if you want to add numbers, the little end is closer. So I'll show you just quickly on this diagram here. With big endian, so big endian, if I want the number here, so this is E, F, G, H, right? If this is big endian. Where's the sign bit? It's on this end. So where is that? It's right at the start. So if I want to find out whether this is a positive or a negative number, I just look at the first byte. It's really close. It's easy. Make sense? Where is the sign bit on a big endian number? It's here. So it's more difficult to access in some sense. Having said that, this number here, A000, if I'm doing addition, where do I start adding from? This end. Yeah? Where is this end? It's right here where I'm starting. So in some senses, that's more convenient. If I'm doing addition with this one, the big endian one, where's my little end? It's on the other end, right? Another thing that might not be so obvious with this one is, look, I've got here 000A, right? If I want to shorten this from 32 bits to 16 bits, what do? I just chop off those 2 bytes. Is it the same number? Is 000A the same as OA? Yeah, there's just leading zeros, right? What about with big endian? I grab these two and I want to shorten it. Is EF the same as EFOO? What do you think? If I just grab these two, EF, those two there, are they the same as EFOO? No, because I'm getting the big end first. The other digits, the other columns are meaningful. Yeah? So it's more difficult to translate or to shrink this big endian than it is to shrink the little endian. And again, these are particular cases where one might be better or more efficient than the other one. Here's an example, hopefully, that puts it together. There's again a struct, so a box with stuff in it. Let me just draw the thing. I think it's easier if I just draw on it than talk to it. So we've got a struct. It's a box that glues together some things. I've got a character, and actually this is an array, so there are 12 characters. How big is a character? 1 byte. So actually, even though there are 12 of these, they're separate boxes. They're just 12 separate boxes that I'm working with. Do you remember when I said with the little and big endian, if you only have 1 byte, does it matter which endianness you're using? Doesn't make any difference. It only happens when you have multiple bytes. So in my address, if Jim Smith is in my character array or my string, then it's JIM, the triangle is a space, SMITH, space, space, space. There are 12 blocks. They'll read from left to right. Yep. That's in big endian. Little endian, because each of these is a single byte, it's exactly the same. There is no difference for this character array. The only reason for that is because they're all 1 byte big. If there were 2 byte things or 3 byte things, you would see some differences. So let's have a look at the next one, an int. How big is an int? We said it was 4 bytes. And it's an age. 4 bytes for an age seems quite big. 33 is the age in this case. That turns out to be 0x21. If I look at my big endian location, there are 3 sets of leading zeros, and then there's a 2-1. Did I mention that an int is a very big value for an age? Will you ever really get the first so many digits here? What do you think? Probably not, right? So maybe this is too big. But anyway, we're using an int. What about in little endian? Well, little endian, the little part is at the front, so we got a 2-1 and then those leading zeros. Is it the same value? Yes, it's just written differently. What about department? The department is 260. It's a big organization. OX104, 0104. What about the little endian 04010000? Again, written differently but the same value. So this is fine. If you're reading the character arrays or the strings, you will read Jim Smith. There's no problem. If you're in big endian and you're reading this one, you will read 21, OX21. If you're in big endian and you read this one, what will you get? You will get this enormous number for the age. Is that the right age? No, it's wrong. It's obviously wrong. Same thing with the department. The department will be enormous. So it really matters that you're reading and writing in the same endianness. Is there an easy conversion? What do you think? Yeah, it's not too bad. You just have to swap the bytes, right? Okay. Moving on to memory and the memory hierarchy. So that was a little bit of technical stuff. This is a little bit more, probably more general knowledge stuff. So you probably already know at least a little bit of this stuff, if not all of it. So computers generally use different types of memory. There's register memory, primary or main memory, and secondary memory. So register memory is really fast. It's in the CPU or really close to the CPU, and it holds the temporary results of calculations. It has to be really fast, and have 23 to 64 registers. You don't have many registers. Primary or main memory mostly resides on the motherboard, includes a cache and RAM, and it's used to store current data and code. So this is much more information than what you would put in the registers, and it's about 100 times slower than the registers. Secondary memory is the peripheral devices like disk drives and so on, and it's much slower, and it's used for long-term persistent storage. So when you turn off the machine, right, the memory that's on board, it gets wiped. When you turn off your machine, you want the stuff that's on your hard drive to stay there, so that when you load it up next time, you can actually access it again. It's many thousands of times slower than register memory, and it's about 1,000 times more capacity than primary memory. So you do get a benefit. It's much bigger, but it's slower, and it's also not volatile, so it doesn't disappear when you turn off the power. Is there also a tertiary memory? Yeah, off-site kind of storage where you've got like a library somewhere that you might have to access, where you've got backups, for example. They're not directly connected to the machine. Here is a nice memory hierarchy pyramid. Pyramid's kind of nice. It basically shows you that if you go closer to the top, the access time gets slower, you have less capacity, and it costs more. If you go closer to the bottom, the access time is slower, you have more capacity, and it costs less. All right, so the faster you want it to be, the more expensive it's going to cost. All right, it's going to be. In terms of primary memory, it's volatile. That means you must have power. If you lose power, then you lose the data. And it might not happen immediately, but it will happen very quickly. This type of memory is typically called random access memory, or RAM, because it permits individual bytes of data to be accessed, retrieved, and modified at random. You can pick any byte that you want in the memory. And primary or system memory, as it's sometimes called, is divided into a number of different types. We have DRAM, dynamic RAM. There's also variants on these, SDRAM, EDRAM, and a variety of others. There's SRAM or static RAM, which is used for cache memory. We'll talk about caches in a minute. ROM is read-only memory. So it's like RAM, but it's not actually like RAM because it doesn't allow you to change the contents, so it's fixed. The problem with RAM and ROM and the terminology there is that they're both random access. You can access any particular part, but the ROM is the one where you can't change the contents. FRAMs, like flash memory, it's non-volatile technology. Flash memory, USB, memory stick, SD cards, right? And so there's different kinds of ways to store your information. DRAM or dynamic RAM is the most common type of computer memory. It's basically the blocks that you plug into your computer to get your onboard RAM. It's the core of the computer's main memory. It's cheap, it's simple design. It's called dynamic because it has to be refreshed, and basically it's like a little battery. It charges up, and then over time it discharges, and it has to be refreshed with a charge. The system uses this memory to temporarily store programs, data, and processed information, and that information moves around the system. It's normally many times slower than the central processor, so that's an important point. That means that the CPU typically has to wait for it, right? So if you can have this information in a faster piece of memory, that would be beneficial. The system will speed up. ROM and flash memory. So ROM or PROM is read-only memory. There's also EPROMs or EEPROMs, and the data is burnt or built into the ROM at manufacture. It can't be modified, and it contains the information after the power's turned off. So it remembers what you had in there after you've turned off the power. So ROMs are used to store things like BIOS, the basic input-output system, and that system tells a computer how to boot or how to start up. You can also have these flashable or programmable ROMs which you can change. So for example, you can change some of the settings in your BIOS, right? Flash style memory used in USB memory sticks, SD cards. It's not volatile. We're pretty familiar with those USB stick. You plug it in, right? Are they fairly sturdy, those USB sticks? Yeah, reasonably. They're reasonably good. They do have a limit, like a lifetime, how many times you can read and write from those particular things. They're relatively cheap. They're getting cheaper with higher storage capacity. What are we up to these days? What's the biggest USB stick that anyone here has? Are we up to 256 gigabytes? Probably, yeah. So there will be improvements, and the cost has gone down enormously for those as well. SRAM or static RAM, it's built from D flip-flops, so we've seen those before. It doesn't need to be refreshed like DRAM. It's also about 5 times faster, twice as expensive, and twice as physically large as DRAM. So you might say at the start, well, it's 5 times as fast. Why don't we use that? And the other two parts will kind of indicate why not. It's twice as expensive, and it's also much bigger. So if you have a limited amount of space, you would use the smaller one, right? The cheaper one, we don't want to pay as much, and so there are some reasons why we don't use SRAM for everything. Because of its lower cost and smaller size, DRAM is preferred for using computer main memory, and SRAM is used primarily for cache memory because of its speed. So where the speed is really important to us, we will use the SRAM. So caches are much smaller than main memory. They're almost as fast as a CPU, and the purpose of a cache memory is to speed up accesses. And what you do is you get some data that you've recently used and you put it really close to you, so that when you need it again, it's right where you're at. You don't have to go very far to get it. The example down the bottom there is like a cache is really like a refrigerator. Okay, so why do you have a refrigerator at home? Do you have to have a refrigerator? No? If you don't have a refrigerator, what will you be doing every day when you need your milk? You'll have to go to the shop and buy the milk, bring it home. Yep. Is that inefficient? Yeah. It's much more efficient if you buy the milk once, then you bring it home, you put it in your refrigerator. When you need the milk, at least as long as the milk is there, it doesn't take very long to get the milk relative to going to the shops. So a cache is very much like that. If you're going to be using this piece of information relatively soon, or likely to be using it relatively soon, you will bring it closer to you, like in your refrigerator. In this case, it's called a cache. And there may be multiple levels of cache. Yeah? There's a downside to this. There's a couple of downsides actually, but one of them is, what if what if you go to the fridge and the milk is not in the fridge? You have to go to the shop, right? And now you've wasted a little bit of time going to the fridge first, right? So there is a cost to that. Yeah, it's not free. And so it actually takes longer if it's not in the cache and you've checked the cache first, right? So unlike main memory, which is accessed by address, cache is typically accessed by content. For example, I want the milk. So I go and find the milk. Is the milk in there? Yes or no? I'll grab it. So it's often called content addressable memory. A single large cache memory isn't always desirable because it takes longer to search. So modern CPUs will have 2-level caches or multiple levels of caches, right? So they get bigger as you get further away. And some of them may be on the chip and some of them may be off the chip. And to access a particular piece of data, you send a request to the nearest memory, usually a cache. If it's not in the cache, you go to the next cache, until eventually you get to the memory where it's supposed to be stored. Once the data is located, then the data and probably some data around it is copied to the cache, because probably when you're running a program, you're getting this information and then the next line and the next line and the next line. So you might grab a bit in the neighborhood because you're likely to use it in the future. So that's copied into the cache. It's faster to access now. If you make a change to something that's in the cache, here's a problem that you have to address. If you change that value in the cache, has the value in memory changed? The answer is no, not yet. You will have to fix up the memory so that it matches what's in the cache. Does that make sense? Yeah. So there are a couple of complications with this. Here is our modified von Neumann diagram. It's very similar. It just has the caches added. So you'll see there in the yellow box, there's an L1 cache, which is for the CPU. And then there's an L2 cache, which is between the CPU and the RAM. And you'll notice like one of them is slightly bigger probably than the other one. And it, they're put at different levels to provide more access to what do you call it? The cached data. So moving on to secondary memory. Some common secondary memories are magnetic disks, magnetic tapes, optical disks. I'm sure you've seen most of these if you haven't used all of those. Who's never had a look at a magnetic tape here? Everyone's seen a magnetic tape? Yeah. Do we still use them? Yeah, some people still use them for certain purposes, so they're not obsolete, but for most purposes that we used to use them for computing, we probably don't. For example, you won't see a data cassette drive, right, to load games for the most part on modern machines. So none of these permit bytes to be accessed randomly in the same way as main memory. You can't just get to any particular byte. Magnetic disks offer large amounts of relatively low-cost persistent storage that can be accessed really quickly. They're direct access because we access things in blocks, so not just one byte, but a block of bytes or a chunk of information. And that information is on the disk at a particular point. Information is stored on the magnetic properties of the metal surface, metal oxide surface, similar to a tape actually, and it's stored in concentric circles. I'll show you a diagram in a second. If the disk is a metal platter, it's called a hard disk. If the disk is plastic film, it's a floppy disk. So it's not the case that makes that distinction. The disk spins at a really high speed, and there's a head that just sits there and reads the information underneath it. You can move the head backwards and forwards, and so you can change where it's reading. And if you have a higher capacity drive, you might have multiple heads to read that stuff. So here's a diagram of that. Again, I'll just draw on it just to make it clearer, I think. Concentric tracks on each platter are split into between 10 and 100 sectors. So here's a sector. Right, it's a chunk of this platter. A sector contains some number of bytes, let's say 512, and that's called a block. Here is a block. It's a consecutive series of ones and zeros. So that block will be spinning around, right? You'll see that there is a head here attached to an arm, and that thing can move backwards and forwards. So you can move it around. Tracks, so this thing is a track. And because that platter spins, the head will be above a track. Yeah, it's always the same kind of distance away. And so tracks which are above each other form something called a cylinder, right? So they're right above each other. And data blocks are addressed by their cylinder, surface, and sector. So cylinder, surface, and then sector. So you can identify any particular part of this this system by that configuration. When you get a block, this thing, you have a header which says you're about to get some data, right? And then you have the data, and then you have something usually for error correction or error detection to make sure that when you read it, you actually get the right thing. You don't get the wrong thing, or at least you can tell whether you got the right or the wrong thing. Performance, there's various electromechanical properties that determine how fast data on disk drives can be accessed. One of them is obviously how fast it rotates, how fast that head can actually read the information as it's rotating underneath it. You can transfer data a block at a time, and so we have to start at the right point. I think here, the seek time, see this head here, it's not above the track at the moment, so it needs to move this way. Now this is a mechanical movement, so it takes quite a long time actually relative to the digital kind of stuff that we're talking about at other levels. So this is slow. This thing is rotating around, maybe the other way around by that arrow, but whatever way it's going one way. And that means that you have to wait for this thing to appear under the head. So you have two different types of wait time. You have the seek time, which is moving this guy backwards and forwards, and then you have the rotational delay, which is waiting for it to be underneath the head. So the seek time plus the rotation delay is the access time, and then the transfer time is the time that it takes to transfer a block of data from the disk to the controller. They're different measurements for different things. Solid state storage devices, they use integrated circuit assemblies to store data persistently. We're using these more frequently, like the SSDs, the solid state drives. Who's not using a solid state drive? Let me ask that question. I don't see any hands. So most people here would be using a solid state drive, and why would you use one of those? Yep. It's quicker, it's much quicker actually, right? Things boot up faster, right? What's the limitations? Are they more expensive? Smaller, sorry? You can store less information at the moment on the solid state. They're more expensive per byte, right? They will come down in price obviously, but they're more expensive, and they may also be more robust than the hard drives, for example, right? So they have no moving components. That improves the operating life and transfer speed. They're more expensive at the moment per byte than their hard drive counterparts, but you can expect that these numbers will change. Magnetic tape, we still use them. Mostly we use them for routine backup of data, and typically if you have a large amount of data. So when you do a backup, when you load that backup up, do you care if it's sequentially loaded up? Does it matter? You just start at the beginning and you load up the whole thing? Yeah? So as the tape in that example, or that particular problem area is actually alright. So here are a couple of different kinds of tapes. 185 terabytes on a tape. So tapes can store enormous amounts of data, which is one of the reasons why they're really good for things like backups. The other thing, like I said, with a backup is you don't really care that you start from the beginning and go to the end with a backup. You want the whole thing, right? Usually. So a tape is actually really good for that kind of stuff. CD-ROMs, DVD-ROMs, Blu-rays, whatever the next version of those is. The data is stored on the disk by burning zeros and ones into the surface using a high-powered laser to form pits and lands. To read the disk, there's a laser beam that's reflected, and either you can read a 0 or a 1. I'll show you. I think this is a picture. It makes it really simple, I think. Here is my CD. There's my eye. That's the little receiver. You'll notice there are pits and lands. It doesn't matter which one's which. Let's say that I shoot my laser into here and it bounces around here, and eventually you're going to get a little bit of light, right? Because it kind of gets stuck in here. Is that very different to this? Ow. What do you think? Do I get a lot of light now? Yeah. So can I tell the difference between if I hit a pit or if I hit the land? Yes, that's really what we want to do. And so that laser beam is reflected. There's a single track. It's really, really long. It's very slow, relatively, like this laser moving around, that physical thing moving around. The light's very fast, but the actual physical thing moving it is not very fast. DVD-ROM, is it very similar to CD-ROM? Yeah, actually, they're pretty much the same technology in the sense that they're doing the same thing. It's a laser with a shorter light wavelength. It means you can pack more information. You can have 2 layers, so basically you can transition from the top to the bottom layer, so you can have more information, so double the amount of information. You can have them double-sided. Did anyone here ever like the double-sided discs, the CDs? Yeah? They're great for storing more information. What are they not great for? Fingerprints? Yeah, because it's hard to pick it up. Usually one side, right? So you can store a lot of information on these. What about Blu-rays? What do you think? Similar, more information. Yeah. Okay. So in summary for this section, we had a look at addressing and endianness and some of the implications of that. We also looked at primary and secondary memory. And the next section that we'll look at will be data errors. What do we do with those? How do we, first of all, detect them? And then maybe are we able to correct them as well? So that's the end of this section.